Okay, so where do you want me to start? Yes?
Can you do number 25?
I can do number 25, yeah. Oh, okay, sure. Somebody else asked me about this earlier today. Number 25, the three undefined terms of geometry are, Byron?
Point, line, and plane.
Point, line, and plane, that kid. Okay, remember those are the very first three things we talked about in class, and they're undefined because it's hard to define something that doesn't have any thickness or any width, or but we still have to work with them. Courtney? Number 6. All right, so let's do the word. Oh yeah, this is a weird one. I'm interested to see if anybody has any thoughts on this. So it says a 30-foot cable is suspended between the tops of two 20-foot poles on level ground. So draw a picture. There's my level ground.
Which one's this?
Number 6.
Oh, I got 28 posts.
Okay, that's number
Oh, shit.
4.
Got 15 feet.
Okay, we'll talk about it. You're close, but not quite. So there's my
All right,
two.
now we're gonna have problems.
Okay, I'm okay with that. There's my two 20-foot posts, and I have a cable strung between them. And what you need to understand is that the cable has weight, and so it's not. I mean, it's flexible a little bit. It's not rigid, and so it's going to sag. And this cable is sagging so that it is 5 feet off the ground at its lowest point. All right. Oh, and we also know that the total length of the cable, not the distance in between them, but if I laid the cable flat on the ground, the length of the cable is 30 feet. So the question is, how far apart are the two poles? And it seems like a question that's impossible to answer because you don't know how much it's sagging. But there is a way that you can figure it out. It does not have to do with the Pythagorean theorem. That's a nice guess, though, because we kind of have some triangles in here that you could do that with. Does anybody see anything kind of fishy about this? It's a parabola, right? But it doesn't have anything to do with that either. It's not even that complicated. Golden?
It's sagging, so I can't see it.
Right, okay, so the key there is, and that's why I thought Byron might have had this a little bit, if there's 5 feet between where the cable is the lowest on the ground, how many feet is there between here and the top of the things? Yeah, 15 feet. Okay, oops, not 15 inches, 15 feet. So if it's 15 feet from where the cable is at its lowest point to the top, how long is the cable again? 30 feet. How much distance can there be in between the two poles for it to be able to sag down 15 feet and then back up 15 feet? If it goes down 15 feet and it goes back up 15 feet, how far this way can it go if it's 30 feet long pole? 0. Yeah, can't go anything at all. Because if it's 15 feet down and then 15 feet back up, if I stretch it out at all, it's going to have to be longer than 30 feet, right, to get that distance between it. So yeah, it's kind of a trick question. So the answer is that the poles have to be basically right on top of each other. The cable is hanging straight down 15 feet and then goes straight back up 15 feet. And there can't be any distance in between them where the cable would have to be longer. All right? So yeah, 0, basically 0 feet. The poles have to be touching. Okay? Number 15, is that one of the graphing ones? Oh, no, okay, good. This is a good one. All right, so for 15, they give you a couple of different diagrams, and you are asked to figure out, first of all, which lines are perpendicular. So let's take it one diagram at a time. So for this one right here, for that diagram right there, what two lines are perpendicular to each other? Byron?
CP and
Okay, line CP is perpendicular to line AB. How do you know? Yeah, because there's a little right angle symbol right here, okay? And that's really, 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 really important, because then the next question is line AB perpendicular to line DQ? Not necessarily, okay? It looks like they are, but can we assume that two lines are perpendicular just because they look like they're perpendicular? No. So the only ones that you know from sure from this diagram are the ones Byron said, line AB and line CP. Okay, we'll do the other ones in a second, but based on that, what lines up here are parallel?
That's about all.
That's it. None. We can't tell. Okay, these two look parallel, but do they have the little parallel markings on them? No, so we can't assume that they are. So in this first diagram, the only thing that you know is that line CP, this one right here, is perpendicular to line AB. Okay? All right, so let's take a look then at the next one that they drew. So now we have one line going this way and two this way, and these are marked up. G, H. Okay, what lines in that diagram are perpendicular?
Oh, perpendicular?
Uh-huh.
None.
None. Because there are no little perpendicular marks right there, so even though they look like they are, we can't say for sure that they are. Okay? What two lines are parallel?
E and G.
Yeah, we need to use two letters.
Yeah.
Okay, so now for this one we can say that line EF is parallel to line GH. Okay, and that's because it specifically is marked so that we know that that's true. Okay? So now save me the trouble of doing the drawing. If you look at the next diagram, what two lines are perpendicular? Byron?
JK and IK.
Right, J and K are perpendicular, and I and K are also perpendicular. Okay? In the next drawing, because there's little right angle marks on both of them. Which ones are parallel? What's that?
I and J.
Do you want to say I and J because?
If they're both perpendicular in the same line.
Right, right. And we haven't really proved that yet, and we'll talk about that. So you can go either way on that. You could say that I and J are not parallel because they're not marked such that they are, or you can say I and J are parallel because of what you just said. So I would take either one on that. Byron?
Can you do number 10?
Are we done with 15?
Yeah.
Yeah? Okay. All right, number 10. Okay, number 10, we're going to make another Venn diagram, and these are the words we're going to use. Triangles, trapezoids, polygons, obtuse triangles, quadrilaterals, and isosceles triangles. All right, so I'm going to start out by making a great big circle. Out of those 6 words, what is the most general? Polygon. Okay, so this whole big circle is going to be all of my polygons, because everything up here is a polygon. All right. Then inside the polygon circle, we need a triangle circle, and we need a quadrilateral circle. Do the quadrilateral and triangle circles intersect at all? No. There's no such thing as a quadrilateral that is also a triangle or the other way around. So it doesn't matter which one you call what. We can make this quadrilaterals and make this triangles. or you can go the other way around. So we're done with those, and we're done with those. Okay, where do the trapezoids go? Inside the quadrilateral. So here's my trapezoids. Anything else that needs to go inside the quadrilateral?
No.
Nope. Okay. So obviously the obtuse triangles and the isosceles triangles are going to go inside the triangle circle. What do I need to do with those two circles? They do need to intersect, because you can have a triangle that is both isosceles and obtuse at the same time. So somehow or other, these two things need to intersect. So we'll go obtuse triangles and isosceles triangles. So that's what that's going to look like. And you can use ovals, or you can make funny shapes to make it all fit. That doesn't really matter. Just as long as they're inside the right beams and overlap the right way. Brianna? I can do 11. Okay, number 11. So this is kind of a strange one. You have a road, and this road runs north-south, okay? And then you have a nice forest over here. Thank you. And you have Beth Mack and her dog starting in the forest, and they are, we know, the dog's name is Trouble, that's right, 15 kilometers from the road. And they're trying to get back to the road. Maybe they don't really know quite where the road is, or I'm not really sure what's going on, but instead of walking straight to the road, what they have decided to do is they are going to walk south 1 kilometer, walk south this way, and then they're going to walk north 1 kilometer. So this is 1, and this is 1. And then Beth Mack must be a math major or something, because she's going to do a little pattern. Now she's going to go south another kilometer, and then she's going to go to the west 2 kilometers this time. Well, it's not surprising, because it's a strange problem.
And then down 1 and over.
Right, and so the question is, the first thing we need to figure out is how many times does she have to do this before she'll travel the 15 kilometers over here to the road? How far west has she gone so far? 3, so she needs to keep going. So she'll go down 1 and then this time over 3. Is she there yet?
No.
Okay, so she's got to play the game again. Down 1 and over this time 4. Is she there yet?
Nope.
Because she's only gone 4, 7, 9, 10 so far to the west.
5.
And so now she'll be in good shape if she goes down 1 and then over 5. Now she'll be at the road. Okay, so that's the picture that we're looking for. Now we have to use our picture to solve the problem. How many total kilometers did she travel with her dog? 20, yeah. 1 plus 1 is 2, plus 1 is 3, 5, 6, 9, 10, 14, 15, 20. So they traveled a total of 20 kilometers. How fast does it say
4.
she and her dog are traveling? 4 kilometers per hour.
Divided by 5.
Yeah, so if you divide these two, how many hours does it take for them to get back to the road?
4.
5 hours. 20 divided by 4 is 5, so it's going to take a total of 5 hours. So if they leave, or if they start walking at 3 o'clock, what time will they get to the road?
8.
8. What time is sunset?
7:30.
7:30. So yes or no?
No.
No. Okay, so should have walked faster, or maybe more direct, or I don't know what. They're not going to get there. Yeah, don't know what's going on there, but maybe they, like I said, maybe they just didn't know if there was a road. Maybe they needed that kind of, I don't know. maybe they're exploring, yeah. They're not in trouble. All right, anything else? Gillen? 13. Okay. Are those your pages?
I wasn't seeing that.
Oh, no, now they're there. There was a little computer glitch. Okay, so number 13. So we're going to start with a triangle, and we know that the vertices of the triangle are at 0, 3, 4, 1, and negative 3, 1. So here is our pretty little triangle. And then we're going to, oops, I don't want that filled in. We're going to take that triangle and we're going to flip it over the what? Y-axis in this case, okay? So Gillen, y-axis is this guy right here, right? So where does this point go? Gillen. If I flip that over the y-axis. It's good. I'm going to flip it over the y-axis. So it's kind of a trick question. I'm setting you up. It's on the y-axis, so does it go anywhere? No. So that's going to stay right there, okay? How about this one, Gillen? Where does this one go if I flip it over here? How far is it from the y-axis to the right? 4. So how far will I go to the left? Okay, so this would be 1, 2, 3, 4 over there. And that's why that point stays right there, because it was right on it, so it'll stay on it. How far is this one to the left of the y-axis? So it'll go 3 to the right, okay? And so my new shape will look something like this. And what do we have to do? Find the coordinates of it? So can you see that that's just the same thing flipped over? So this one stays at 0, 3. This one is now at 3, negative 1. And this one is at negative 4, 1. Okay? Did they ask you about congruent or anything? Or? Oh, okay. No, that's it. What did you say?
Then you multiply each x value by negative 1.
That's how you got it. Okay, good. So, yeah, one thing that you might notice is that there's a pattern between the old coordinates and the new coordinates. And we say what that is again?
You multiply each x value by negative 1.
Okay, good. So all the y values stay the same because they're staying on the same level, and the x coordinates get flipped to the other side, so they all get changed by positive or negative 1. All right? Okay, you're starting to pass them forward already. Are you good? Well, don't pass them forward. We're going to correct them together. Okay, are you done with your questions? Okay, will you exchange your papers and we will correct them together?